Okay, so we will be get the next chapter will be a JFET. Okay, that will be the last important one. We have to get through it, and then we will get more time. I will go with you to guarantee you know how to using your meter, oscilloscope, or generator in order to do the lab. This week we will get a quiz on Wednesday that will be concentrate on the active filter. Okay, I could quickly go over on the filter. Active filter, that means they will be build the filter with the op amp, okay, and also RNC, RCL circuit. And basically, for this amplifier, you get input at 10 volt. If the gain equal to 1, then the output will be also 10 volt, okay? And if you take the voltage gain equal VL divided to Vin equal to 1, if you want to calculate it into the decibel, then you take a 20 log of 1, you get a 0 dB. Now, what that means for 0 dB? 0 dB, that means no loss. You get 10 volt coming out, and you with the 10 volt coming in, okay? And also, you have to know what about critical frequency. You know, that is the frequency, the output will be going down to 70.7% of the maximum value. In this example, maximum VL equal 10 volt. So at the critical frequency, okay, then the output will be going down to 7.07 volt, or they can say going down to minus 3 dB. Minus 3 dB, that's equivalent to 0.707, okay? On this one, they just give it to you, the sine wave and the square wave. Basically, the square wave will be make it up to different sine wave at a different harmonic. in this example, they give a fundamental harmonic, and then you get a third harmonic and fifth harmonic and a seventh harmonic, okay? More harmonics that make it up the square wave. So if you're looking the cell sideways on the oscilloscope, you can see only one side wave. And also for the square wave, same thing. However, if you're looking on the spectrum analyzer, then you can see the square wave, they can make it up by too many harmonic of the sine wave, okay? And also, they can asking about the bandwidth. Basically, the bandwidth by basic definition should be equal F maximum frequency minus the minimum frequency, okay? And this is they just display for you to see on the oscilloscope. You can see 1 kilo square wave, okay? And also, they will be same time display 1 kilohertz on the square wave on spectrum analyzer. What is the difference between the oscilloscope and the spectrum analyzer? Oscilloscope is a time domain. That means the signal vary with the time. Oscilloscope.
Mr. Fairman, if possible, can you make your screen a little bit bigger?
Bigger?
Yes, please.
Let's see.
It's kind of cut off.
Smaller.
Smaller.
Okay, that worked too.
Yeah, that's what I can do. Okay. Basically, if you're looking at the sine wave, a square wave on oscilloscope, this is the time domain vary with the time. Okay. So you can see only one square wave. However, if you're looking at the frequency domain for spectrum analyzer, that will be the frequency domain. Signal vary with the frequency. Then you can see a lot. First thing, you can see a fundamental, okay? And next will be a third harmonic, fifth harmonic, okay, and seventh harmonic, and so on, using only odd harmonics. So on the spectrum analyzer, you cannot see any square wave, okay? Only thing they display the signal at a certain frequency and what the amplitude supposed to be, okay? This is just repeat the same thing, okay? So when they asking you what is the bandwidth for 1 kilohertz sine wave, okay? So the answer will be 0. The thing is 1 kilohertz sine wave, maximum is 1 kilohertz, and minimum also 1 kilohertz. So 1 minus 1, you get a 0. However, if they can asking you what is the bandwidth of the square wave, then the answer, you have to be asking for what harmonics they want to go to maximum. If they say fifth harmonic, okay, then that's why you're able to do your calculation. Fundamental harmonic for 1 kilohertz. Third harmonic will be 3 kilohertz. Fifth harmonic will be 5 kilohertz. So the bandwidth will be 5 minus 1 equal 4 kilohertz. Okay. Normally, technician, you will working up to only 13 harmonic. And for the technician, no matter what, you have to know how to working with that equipment. Okay. On that equipment we get in the lab, that will be helping you to learning, to exercise it, to guarantee you know how to using it. Okay. Then when we're talking about the filter, like the definition, they allow passing some signal and also blocking another signal. Okay, that is the basic of the filter. Active filter, they're using the transistor or op-amp, mostly they're using the op-amp. Combined with the passive RCRL, RCL. Try to understand, they're using the active component for the gain, okay? However, for RCRL, RCL circuitry, that's what we call a passive component we'll be using for the frequency, okay? Active device provide voltage gain, and the passive circuit provide the frequency selectivity. The four basic for the filter will be low pass filter, high pass filter, band pass filter, and band stop filter. Also the not the name, not filter. Okay, so now they display this is the low pass filter. Okay, low pass filter means they pass any frequency less than the cutoff frequency. Okay, this is a cutoff frequency FC right here. This is a display for ideal, okay, band pass filter. And another one they will be displayed for the practical low pass filter. Okay, so basically we're working with the practical filter. So at this point in here, you going down, you get the cutoff frequency, and you go to the left, they say minus 3 dB. Okay, that means at the cutoff frequency, the output will be going down to minus 3 dB. I given you the example. You get an input 10 volt, output supposed to be 10 volt. However, at the cutoff here, they will be going down minus 3 dB. And minus 3 dB equivalent to 0.707. Then you can calculate it into the voltage. That means you take 10 times 0.707. So you can get at this point here will be minus 7.07 volt. Okay. And also we're talking about the bandwidth. Bandwidth of the low pass filter will be from 0 up to cutoff frequency. Okay. And also when they say slope equal minus 20 dB per decade, what that means? That will be telling you if you increment frequency cutoff 10 times. For example, if the cutoff 1K, 10 times will be 10K. then the output will be going down 20 dB per decade. 20 dB per decade is not telling you what the voltage you want. If you want to know what the voltage is supposed to be, you have to know what the minus 20 dB equivalent to numerical value. That will be 0.1. Okay? So basically, they're going down to 10 FC, and the output, they will be going down from 10 volt to 1 volt. Okay, that's a low pass filter. And the formula to calculate the cutoff frequency. Formula will be Fc equal 1 over 2 pi RC. Okay? In this formula, F will be in Hertz, R in Ohm, C in Farad. Okay? At cutoff frequency, the gain down minus 3 dB, or the output going down 70.7%, same as 0.707 of its maximum value. After FC output decrease at a constant rate as the frequency increase, that is, when the frequency increase tenfold, 1 decade, the voltage gain is divided by 10. In other words, the gain decrease 20 dB each time the frequency increase by 10. Okay? 1 pole, 2 pole, 3 pole. 1 pole low pass filter, that means in the circuitry they get only 1 R, 1 C. And the roll-off rate will be minus 20 dB per decade. Or that will be 0.1. 0.1, we get the thing, we take a 20 log of 0.1, you get minus 20 dB. 2 pole, then you get 2R and 2C. The roll-off will be minus 40 dB, or 0.01. 3 pole will be 3R and 3C. Roll-off rate will be 60 dB per decade. So the best will be in this given to you will be minus 60 dB per decade. That means they will be cut off quickly. Okay? And this just given to you a little more detail on that low pass filter. Okay? And now you can see this is display for the 1 pole, 2 pole, and 3 pole. So basically you get the ideal will be right here. This ideal. And 60 minus 60 dB will be close to the ideal. That means much better. Okay? So they will be going down with 60 dB per decade. This one we already done before, okay? They given you the circuitry of 1K, 1R, 1K, C 0.1 microfarad, input will be 10 volt IMS. They want to know the calculate the gain of the circuitry, okay? They can using the op-amp here to build the filter, okay? The op-amp, we already get through it. They can be inverting amplifier, non-inverting amplifier, or follower. In this example, they're using the follower, okay, to build the filter. Follower, that means output following the input. So the gain equal to 1. Now they're adding R here and C here, make it to be a low pass filter. And the cutoff frequency 1 over 2 pi R times C. So number one, the gain of the op-amp will be 1. The thing is follower. Cutoff frequency, we substitute the value I and C into the formula here. We get 1.6 kilohertz. Okay. And also they want to know what the Vout at the 1.6 kilohertz. Okay. At the cutoff frequency, output going down to 3 dB. That means 0.707. You take the Vout 10 volt times 0.707, you get 7.07 volt IMF. And they asking about what the output at the 10 time of FC. At 10 time of FC, the output will be going down 20 dB. 20 dB equivalent to minus 0.1. Okay, minus 0.1. So they will be 1. Okay, take a 10 volt times 0.1, you can get 1 volt. That is how to calculate the output of the filter at the cutoff frequency or at the 10 time, at the cutoff frequency at another 10 time. Okay, also this will be a low pass filter. The one I given, I review for you. That means you suppose you can do it right away without open any notebook or textbook or anything. Okay, that's just a very, very basic. Now, first thing you can see, we get R here, C here, we know that low pass. Okay, when they change the position for C and R, that will be high pass. That's easy to recognize. And now they're using this op-amp here, amplifier here, will be non-inverting amplifier. That's what you need to recognize. Okay, and a non-inverting, the gain will be 1 plus, in this case will be R2 over R1. Okay, and cutoff frequency, you can calculate the formula 2 pi R times C. So now they give an input 2.5 VIMF. They want to know the gain. The gain again, 1 plus R2 over R1 in this example. And that you get a 10. Okay? And the cutoff frequency, you're using the formula 2 on FC equal 1 over 2 pi R times C. Calculation given to you 159 hertz. Okay? And now they want to know what is the maximum output. Input is 2.5 volt. The gain equal 10. Then the output will be 25 volt IMX. And they are asking Vout at the cutoff frequency. At the cutoff frequency, the output will be going down 3 dB. That means 25 times 0.707, you get 17.68. And also got the Vout at 10 times of cutoff frequency. You take 25 times 0.1. Okay? Get any question or anything? understand the first one, the next one filter will be more easier. Same thing. Now, this is a high pass filter. High pass filter will be pass any frequency with the cutoff higher than FC. So, same thing. This is the cutoff right here, okay, FC, okay? And when you're going down 10 times FC, they will be also going down minus 3 dB. And the bandwidth for the high pass filter will be from the cutoff go to infinity here, okay? And also formula to calculate the cutoff frequency is still only one formula, 1 over 2 pi times R times C, okay? And for this example here, they given you input to VR met R 910 ohm, C 0.1 microfarad. They want the gain. They using a follower, gain equal to 1, okay? And the cutoff frequency using the formula 1 over 2 pi times R times C. That given to you 1.75 kilohertz, okay? And V out at the cutoff frequency, you take the maximum output times 0.7, 0.7. Okay? Exactly the same thing for the low pass. Okay? That one you supposed to do it. Okay? At the high pass, they using inverting amplifier. Okay? So I just quickly make sure you can get the AC AV. What AV equal? The gain of the op amp
minus R2 over R1.
minus that is what you can get the gain. Okay? That's what we already given to you right here. Minus R2 over R1. Okay? And if you want to calculate the cutoff frequency, also you already get the formula here. Same thing. 1 over 2 pi R times C. Okay? If the input 1.5 volt IMS and the maximum output, you can get the gain time with 1.5 V IMS. To get the cutoff frequency, they will be 1 over 2 pi RC. V maximum, that means you take input 1.5 volt IMS time the gain, okay? And V out at the cutoff, that means you take the V out maximum time 0.707, okay? And V out at the 1.59 kilohertz. I believe that maybe 10 times of the cutoff. Then you take the maximum output times 0.1. This is just a two pole, okay? You're looking in here, you get a C1, C2, 2C, R4, R3, QR. That means two pole. Very, very tough to recognize three pole or more Okay, the circuitry very complicated. Okay, only for the engineer they can go into the detail. For us technician, when you testing the circuitry, engineer already telling you what they want at the output for what input, what the cutoff frequency, and you can measure to verify what they wanted, but you don't have to do any calculation. Okay, even the engineer test or test engineer, we don't have to do any calculation. Only thing is what they want at a certain point on the circuitry, what voltage they want, what frequency they want. They telling you, okay, and you only measure to verify is it a right or wrong, okay. And the bandpass filter. The bandpass filter here, you can see basically bandpass filter they combine between high pass then low pass. That make a bandpass. Okay, they adding a high pass to a low pass make a bandpass filter. If you look in here, they show right here. Okay, first thing this is a high pass, and this will be a low pass. So that will be make it to be a bandpass filter. Bandpass filter, okay, and they get the two cutoff frequency, not one. Okay, one they call FL, or the other one called F high. Some different they call F1 or F2, doesn't matter. So the bandwidth of the bandpass filter will be the difference between F high and F low. Okay, that's a bandpass filter. This gives you a little more detail, okay, for the frequency output here, okay. Pass band will be from the F low to the F high, and this is the F center, okay. So also they can tell you right here, pass band FC over F low to F high. Over F high, they will be stop band, and up less than FC, they will be stop band. They allow only frequency signal going between F high and F low. They just a different circuitry, okay? They must be telling you what the name of the circuitry, otherwise cannot recognize. And a band stop here. Band stop just the opposite to the band pass filter, okay? That means any frequency higher than F high allowed to pass, less than F low allowed to pass, and they block any signal between F low and F high. So just the opposite to the band pass filter. Okay, so on this section here, they given to you the difference between a one field section, one pole, 2 pole, 3 pole, 4 pole. So basically the best one will be the 4 section here. The thing is they will be lower narrow band. Narrow band means will be get less noise, okay? And sometimes they can ask you for this output of the low pass filter, different engineer design, best cell, butterworth, elliptical, and cavity. So which one you think is a good one? Okay, first thing you understand is you get that one here. They call a ripple. That means the noise. Noise means the unwanted signal. Okay, so if you're looking on this display, the best for the cutoff will be capacity right here. They will be cut off close to the ideal. However, capacity they get noise. Okay. So what happened to elliptical? This guy here. Okay. So they get a lot of noise. That's not really good. But the worst, that's okay, no noise. Okay. However, the slope will be higher than best cell. So in this example, best cell be the best. Okay. First thing is they don't have any noise in the mid range. Okay. And also the cutoff will be better than the worst. Okay. That one, try to different one. We already done that thing here. Okay, now this one, you have to memorize something. Bandpass filter. Bandwidth, okay, will be FC2 minus FC1, okay, right here. And Q will, that means the quality of the filter. To calculate the Q, you equal F0. That means F at the center divide to the bandwidth. Okay. So that Q will be quality factor of the bandpass. Okay. If Q you calculate greater than 10, that's what they call a narrow band. Okay. Narrow band will better than wide band. Okay. Q less than 10, they will be a wide band. Okay. Depending on what you get for the Q. So that's the band stop filter. Okay. So Wednesday you get the crease will be covered on the filter. So make sure you review that and you're able, okay, to get that through. Okay, let's see. Okay, any question? Then we can go to the next one.
I have a question about the filter, Mr. Pham.
Right?
Can I ask you a question about the filter, the last chapter that you was?
Okay, go ahead.
Is there a benefit using an inverting versus non-inverting low pass or high pass, as you show in your previous slides? Basically, you showed that it's possible to build, for instance, a high pass in a non-inverting version or an inverting version. So is
that only telling you they can build low pass filter or high pass filter or band pass filter, doesn't matter, using amplifier. And amplifier, they can be follower, they can be inverting amplifier, they can be non-inverting amplifier. Okay. They
Okay.
can be any
Okay. Okay.
if they want. Okay, B, we already done with the bipolar transistor. We already done with the operational amplifier. And this is a last chapter really for every technician must be understand. That's a JFET. Okay. And we still get few things to complete for the program like you can get for the comparator, okay, differentiator, integrator, and few different circuitry, but that's not major, not really important. They not too much. The JFET, that stands for junction field effect transistor, is a type of FET that operate with a reverse bias PN junction to control current in the channel. Depending on their structure, they fit fall into either of two categories, N channel or P channel. In the bipolar transistor, also you can get N, PN, then PNP. So in the JFET, they also get the two channel. One they call an N channel and they call a P channel. This is the symbol for the N channel. Okay, you get the drain and you get the gate and you get the source. Okay, like the same thing bipolar, right? You get the bay collector emitter. In JFET, they get the gate, drain, and the source. N channel, and this is the P channel. The difference is the arrow point in and the arrow point out for P channel. Okay, and this will be a display physical for P channel and the N channel. Okay, so N channel will be on gate and the drain they will be N. Okay, a channel will be P channel. Okay, and N channel will be a positive P channel, P here, but that will be N. Now we see DC bias N channel JFET. VDD, that means the voltage here. Okay, on the bipolar they're using VCC. VDD provide the drain to the source voltage, okay, and supply current from the drain to the source. So this will be voltage here, supply the current flowing from the drain to the source, okay. VGG, that means this is the VGD here, set the reverse bias voltage between the gate and the source. Okay, this is the gate and this is the source right here. Okay, JFET is always operate with the gate source PN junction reverse bias. That means the diode, they will be reverse bias. Now, first thing I try to see what's going on here. If you're looking on this first, okay, This is the voltage they measure the VGS. That means the VGS means the voltage from the gate to the source. And this is will be a measure the current going from the drain to the source. So when you say on the display the measure VGS very more negative, okay, then that's why they can give the current ID here, okay, a little. You compare this one and this one, okay. This one VGS will be less, then the current ID will be more, okay. And this is the channel for the electron moving. Current flow, the thing you get electron moving from the drain to the source, okay? This is the channel when they will be so narrow. That means the current will be less. This one get a little bigger, so the current will be more. So that's only telling you one thing. If the VGS less negative, then you can get more current, okay? If a VGS more negative, then the current ID will be less, okay? And also that will be showing you the symbol for the JFET when you're working on the lab. Reverse biasing of the gate source junction with a negative gate voltage produce depletion region along the PN junction, which extend into the N channel and thus increase its resistance by restriction the channel width. That means that resistance in here, big resistance, you get a less electron moving, less current, okay? Now, on that one, less VGG, that means the voltage here less, then the current will be more and the channel will be wider, okay? So more electron can be moving, that means more current for the current ID. Okay, now we see on that one, they will be display the relation, okay, between the current ID and the voltage VDS. So this is a zero ID and also zero VDS, okay? Then when you're going up to the voltage VP, that's what they call a ping off voltage, okay? When they start at a VP, and now you're looking in the lab, you can get the current ID equal IDSS. That means the maximum current, okay? And then after that point, the current will be constant, okay? No changing. That will be at the VGS equal 0. That means VGS equal 0, then the current ID will be equal maximum current. They call IDSS. Then at a certain point right here, okay, when the voltage keep going up to the point they call a breakdown, okay, this is a breakdown. So basically when you're looking into this graph in here, okay, you can see the JFET will be working in the three area. First area, from 0 to VP, they call an ohmic area. What that mean, ohmic area? That means JFET can be using as a resistor, okay? Then from the VP up to the breakdown here, this area they call a saturation, okay, or constant current area. That means in this area, the current ID will be equal ID at S. And the last one will be a breakdown. That will be cooked the JFET. Okay. Now, this is more detail. The maximum drain current out of JFET occurs when the gate source voltage is 0. That means when VGS is 0, then you get the maximum the drain current. The drain current is almost constant in the region between VP and VDS maximum. If the drain voltage is too large, JFET breakdown. JFET act like current source when it's operating along the almost horizontal part of the drain curve, mean between VP and VDS maximum. The minimum voltage VP, they call a pin off voltage. VP stands for pin off voltage. The maximum voltage VDS max, they call a breakdown voltage. Between the pin off and the breakdown, the JFET act like current source with the value of IDSS. IDSS stands for the current from the drain to the source with the shorted gate. Shorted gate, that means VGS equal 0. Ohmic region, the almost vertical part of the drain current, called ohmic region. That equivalent to saturation region of the bipolar transistor. Cutoff voltage. The value of VGS that make ID approximate 0 is that they call a cutoff voltage, VGS off. Okay, the question is what is VGS off? That means at VGS off ID approximately 0 ampere. The JFET must be operated between VGS equal 0 and VGS off. Comparison, pin off and cut off. VP is the value of VDS at which the drain current becomes constant and is always measured at VGS equal 0. VGS off and VP always equal in magnitude but opposite in size. So data sheet normally given either VGS off or VP, but not both. If I say VGS off equal minus 8 volt, then you must be understand VP equal plus 8 volt. Okay? They opposite, but the value must be equal. So on the data sheet, they given you only one, not both. So basically that's a combine everything. You must read it 100 times. When they asking you, you can know right away. Okay? Now, this will be display relation between ID VGS and VDS. So now, if this point right here, what VGS equal? Telling me.
-1 volt.
Equal what? What VGS? minus
-1 volt.
negative 1 volt. If you want ID, go into the left. This point right here will be ID. And if you want VDS going down, you can get VDS. So basically, the current ID of VDS vary depend on the VGS. VGS equal 0. ID equal IDSS. Okay? And you going down here, VDS equal VP. VP naught. Okay? And depending on the VGS, then you can get a different ID of VDS. So JFET will be called a voltage controller device. That means you changing VGS, you changing ID, you changing VDS. Okay, make sure you have to understand. JFET is a voltage controller. NPN-PNP bipolar transistor, that will be a current controller. The thing is on the NPN-PNP, you get the formula IC equal beta times IB. So when you change the current IB, you change the current IC. So that's what they call current controller. Okay? JFET is a voltage controller, but bipolar will be current controller device. So that's why we already put in here. Okay? Make sure you have to read it. Now, they try to show you at the cutoff voltage. Okay, that means they measure the voltage at the gate in here. They say V at the cutoff. When they measure the current, with the current ID will be 0. V at the cutoff. Okay, that means VGS at the cutoff, you don't have any more. Okay, channel here to go. They will be open. So no current flow. So remember, at cutoff voltage, ID equals 0. And VGS must be equal VGS off. That's what they show you here. The basic operation of a P channel is the same as the N channel, except P channel will be required VDD is negative and VGS will be positive. That's the difference between N channel and P channel. Like the same thing, NPN, PNP, mostly they're using NPN. And also JFET, most time they're using N channel. Now, for the JFET circuit show, given VGS off equal minus 4 volt and IDSS equal 12 milliamp. They want to know the minimum value of VDD required to put the device in the constant current area operation. Okay? So now they given you the JFET circuitry and channel. And they given you RD 560 ohm. And they don't know what VDD equal. However, they given you VGS of equal minus 4. And also they given you IDSS. So what is the IDSS? IDSS, that means the maximum current, okay? And in the constant current area, they want to know what the minimum. In order to do it, first thing you need to know what the ID in the constant current area. We already said it before. This is the constant current right here. And the value here for the ID. And that value ID at that. What the value here? This VCE. This will be VP. Ping off. Okay. So now they asking for, if I want, they will be in this area. What the VDD supposed to be. Okay. So first thing you understand is the current ID flowing here. If you want it to be in this area, then ID must be equal ID at X. That means equal 12. Okay. Now, if VP, let's say they given you what? VGS of. VGS of equal minus 4 volt. Then what VP equal?
4 volt.
Will be plus 4 volt, right? We already said VGS of and VP will be get the same value, but opposite. So if VGS of equal minus 4, then VP equal 4. Okay? So they can explain to you here. JFET to be in its constant current area. VDS equal VP equal 4. Okay? That's the thing they given you VGS of equal minus 4. Constant current area VGS equal 0. ID equal IDSS equal 12 milliamp. So now they want to know what the voltage drop here. Okay? You already know the current will be IDSS 12 milliamp. You get 12 milliamp, you times 560 ohm. Okay? So you get 6.72 volt. That means the voltage across RD equal 6.72 volt. Okay? And now this voltage for the power supply here will be equal the voltage across RD adding to the voltage VDS here. And VDS, you understand, they equal 4 volt. That is VDS right here. Okay? So they take the 4 volt adding to 6.72 volt. So the power supply is supposed to be minimum 10.7 volt. if the student can understand this problem, that means you really understand a little more from at the beginning up to this point. Again, they given you the circuitry with the input VDD, okay? And they don't know what the minimum VDD in order to support for the circuitry, okay, with the output working between constant region. That means this area only, okay? So if at this area, constant region, okay, they stuck at the VP. That means VDE, sorry, must be equal VP, okay? And also the current must be equal IDSS. That's why they calculate the voltage drop across RD, okay, with the current IDSS. Then they have to know what the voltage from the drain to the source. That means VDE. In this case, they equal VP. Then they adding those voltage to get the requirement.
Mr. Pham, where do you get the E from? Are you thinking about bipolar or something? We only had drain, source, and gate.
There, drain.
So where do you get the letter E from? Like VDE. What is the E?
VGS.
Oh, you got, well, oh, so where you wrote VDE, you meant to write VGS.
Yeah, that's VGS off.
Okay, once again, what I'm asking you, where you wrote the VDE, you meant to write VGS, is that correct?
VGS, sorry. Thank you.
So you need to erase that VDE out and put VGS there.
Yeah.
VGS off.
VGS, not off.
Not off?
That's the VDS, right?
VGS. You got VDS or something. Whatever, Mr. Pham, you got the wrong thing written down.
Yeah. That's the VD. Okay. That's the VD. VDS. Okay.
VGS, not DS.
DS, not D.
Drain.
GS will be going the other way. Now, go back there. Right here.
Mhm. Okay,
Okay.
all right.
Now, on that problem, they say they want to know the minimum VDD in order to get the device working in this area. Okay. To be working in this area, then you know the ID must be the same IDSS. And also VDS, they have to be right here. Must be equal VP. Okay. So when you're going back here, they already gave it to you IDSS equal 12. Then you can calculate the voltage drop right here. Now what you need to know, what the voltage from D to S. Okay. Then you add them up, that given to you the total VDD. In order to get the voltage at the VDS, in order to work in at this area, VDS have to be equal VP. And VP off opposite with the VGS off. Okay, so VGS of minus 4, then VP equal 4. So you know from here to here 4 volt. From drop voltage here 6.72 volt. You add them up, they given you the total voltage minimum requirement by VDD. Now, next one. JFET transfer characteristic curve, okay, for N channel. In order to draw this curve, okay, first thing on this, on the curve here, any point here, VGS will be equal to 0, okay? The thing is this stands for VGS, and this point will be VGS off. So another point, this point for IDSS. When you get the IDSS and you get the VGS off, you can draw the curve, okay? So that's what they call a transfer characteristic transfer for JFET. ID equal 0 when VGS equal. ID equal IDSS when VGS up equal 0. And now, if you're looking on this one here, okay, the first one you already see that before, okay? That means they can change the value of VGS, different VGS, okay? And on the other side, they draw the transfer curve, okay? On this curve right here, in order to draw it, they get the point for VG IDSS. They get a second point for VGS off. Then they can draw the curve. So now, on this curve here, if you're looking on the one point in here, if you want to know ID, you go to the right, okay? So they can be 7.8 milliamp, for example. If you want the VGS going down, minus 1 volt. So any point on this curve, they will be telling you what is VGS equal, okay? And also what is the current ID equal. Now, this is the formula to calculate the ID, okay? ID equal IDSS times 1 minus VGS divided to VGS of square, okay? So basically, this curve is for this equation. That is basically, this equation is not normally will be using for calculation. That's really tough. So that's why they can give you the curve here to help. We'll see. Now, what they given you example. A partial data sheet of the JFET indicates that typical IDSS is 9 milliamp, VGS of minus 8 volt. Using this value, they determine the drain current ID. Again, if you want to calculate the drain current, you using this formula right here. ID equal IDSS times 1 minus VGS divided VGS of square. So the first thing, A, VGS equal 0. What the ID equal? Do you know?
IDSS.
VGS equal 0. What the ID equal?
IDSS.
IDSS. That's right here. That method must be require understanding. Okay? ID equal IDSS when VGS equal 0. So that's why 9 milliamp. And now they say they want ID for VGS equal minus 1. So you must be using this formula. IDSS, okay, time 1 minus VGS off. Okay, they already given to you IDSS equal 9 milliamp here. And you get 1 minus 1 divide minus 8. That VGS off and square. That given you 6.89 milliamp. And you know how to do calculation? C, VGS of minus 4. Then you using the same formula here. Substitute the value and the answer will be 2.25 milliamp. Any question about that calculation? JFET will be more easier than bipolar transistor. If you understand, that require more understanding. Okay, now we get another thing. The forward trend conductance, or they call transfer conductance, GM. So GM will be defined as a transfer conductance, either change in the drain current for a given change in the VGS. Okay, that means GM equal, okay, the delta between current ID and the VGS. Okay, that's a basic definition. However, in order to calculate the GM, then GM equal GM0 times 1 minus VGS divide VGS off. Now, normally, they given you a value of GM at VGS equal 0. That's what they call a GM0. So the question is, what is the GM0? GM0, that means the value of the GM at the VGS equal 0. Okay, so you can calculate the GM equal GM0 times 1 minus VGS divide VGS off. And also GM0, if they're not given to you, you can calculate by the formula 2 times IDSS divide absolute value of the VGS off. Okay, only on this page, I want to make sure you know, what is the GM0? That will be transfer conductance at the VGS equal 0. Or you can calculate the GM0 equal 2 times IDSS divide to VGS of absolute value. Then you can calculate the GM equal GM0 times 1 minus VGS divide VGS off. Okay, so basically, this is an example. Okay, you suppose to do it to see you can get the answer like we do. You calculate GM, you get 1667 microsiemens. Value of the GM will be Siemens. Okay, and also this is just a formula. A certain JFET, they given you IGSS and VGS they want to calculate the input resistance, and that's why you can apply the formula. Okay, so now this will be stopped right here when they will start with the JFETSP bias. Now what I want you to do is try to start with the one we told you to download for, let's see, for the review. Okay, I stop share on this guy. Okay, so now I want to help you to get through that one right here. That you have to download it to make sure you can understand. Okay, number one. JFET is a voltage controller device.
We can't, Mr. Fan, we can't see your screen.
What on number one?
We didn't see your face, Mr. Pru.
Can you say again? I'm not there. Sorry,
Thank you.
sorry. Just 1 minute. Okay, that's what I told you to download the handout. Okay, I go through that thing to make sure you're able to get the right answer, so you can read the handout. You can get a better understanding. Okay, number one, tell me A, B, C, D.
A.
A. That's correct. Okay, number one, will be A. Okay, number 2. Input impedance, JFET. If you're reading on the handout, I can tell you.
C.
What?
I think C. C.
C. The thing that I like to using the JFET, then bipolar. The thing that they get a high input impedance. Now, number 3, the gate control what?
B,
A.
all of the above.
The answer
All of the above.
is
E.
D. The thing is the gate, they will be control the channel. Okay? That means the weight of the channel. And the weight of the channel, that means they affect to the current ID. And also the gate voltage, that will be D. Number 4, gate source diode of a JFET should be forward, reverse, either none of the above.
B,
They will be
reverse bias. B,
they have to be on time reverse bias if you're reading the handout. Number 5, compared to bipolar junction, transistor JFET has much higher than it.
input resistance.
Right, B. Okay, number 6. The ping off voltage have the same magnitude as the
D,
D. Very good.
Yeah.
Gate short cut off voltage, that means VGS off. When the drain saturation current is less than IDSF, a JFET acts like
C.
a resistor. C,
what number? Number 7, right?
7.
C, right?
C.
Right. It look like on the graph display. They get a one area in the first one will be ohmic region and the constant current region. And the last one will be breakdown. Now, this number, channel of JFET in between
B, the drain and source.
right, big, fan and short. You see that is just coming out from the handout. Okay. And number 9 is JFET always operate with
Same question as before.
B.
A,
A, right? They on reverse bias. Number 10. Okay, VGS equals 0. The drain current become constant when the VDS exceeds. Which one?
C.
Perfect. You see that? That's just coming out from the lecture. Nothing. Yeah, okay. Number 11. Okay. Constant current area of JFET lie between
D, pinch off and break down.
okay. D, right?
D. D.
Okay, D. Okay. Now, next one. 12. At cutoff, JFET channel is
B, close out.
A, B, C, D.
B,
B. Okay, number 13. The trend conductance curve is linear, similar, nonlinear.
C, nonlinear.
C.
Nonlinear. 14. Drain conductance increase when the drain current approach.
C, IDSS.
D. Okay, 15. Gauge source diode of JFET should be it also
A.
already know,
B.
right?
B,
B.
reverse bias.
Reverse bias. Last one. The abbreviation of metal oxide semiconductor field effect transistor is
A MOSFET. A.
A.
okay. We'll see. Okay. Try to read it. Make sure you can answer right away. Okay. During this month, we will be get the midterm test. Okay. That means cover everything from the beginning up to this point. We'll let you know when. Only thing is just repeat the same whatever we gave it to you. Okay, any question? Okay, if it's not question, so I will be stop it. Okay,
Okay.
so good night, everyone.
Good night.
Goodbye. Goodbye.
Thank you.
After the long holiday, everyone get tired.